discussing on reactive organic chemistry. Like for example, the first half you have seen where we have looked at stereochemical aspects, like how um, a molecule will be uh, placed itself spatially, and what are the possible arrangements, conformations, all those things, followed by looking at the reactive organic chemistry, for example, like SN1, SN2, addition, elimination reactions, and and like for example, even free radical based reactions and so on. Now, in the last class especially, we were looking at oxidation reactions. So what we discussed about oxidation reactions in the last class is either we can add oxygen molecules or remove hydrogen entities or remove electrons. If you do any such things to carbon, we can make carbon into more oxidized form at the same time where the oxidation state of the carbon increases. So this we have been discussing. And what are the different oxidizing agents with respect to carbon compounds? Like what makes carbon compounds to get oxidized with respect to oxidizing agents? So we have seen different oxidizing agents, particularly two we were having for your syllabus, which is potassium dichromate and potassium permanganate. You all know that potassium dichromate also is well used. Can someone tell me in the class where do we use a chromic acid solution? Anyone in the class would like to comment that chromic acid? I think you must be seeing in the labs, right? In when you're doing in the chemistry labs or something. Chromic acid. Have you heard of the term chromic acid?
Yes, sir.
Yes. So where it is generally being used?
Sir, oxidation reactions.
No, oxidation it is fine, but I'm telling in commonly where you have really used it in all of you. Oxidation, that is for general uh, reactions what I had discussed. But how many of you have at least seen chromic acid in lab when you're doing practicals? I guess everyone or at least few of you. Oh, I don't know whether you people have done by any
Is it chromyl chloride?
chromium chloride. No, no, not chromium chloride.
So red
Potassium.
color, it is in
But
red.
it is
Red color like that.
no color. No, don't worry about the properties. But I hope you have seen, right, orangish or like whatever color will be there.
Yes, sir. Yes.
You all have seen in chromic acid in bottles, right? At
Yes,
least.
sir.
So for what reason you use that chromic acid? Any give a thought or give a like you should think about it, because generally chromic acid is used for cleaning lab apparatus. Is it right? Glassware, especially lab glassware. Everyone agrees for that? Yes.
Yes, sir.
If you have lab apparatus like a conical flask you want to clean before the reaction, or if it is dirty, what you do, if you have grease stains or many whatever such things, you cannot clean a burette and other things like that just like that, but at least to some extent where there are a lot of stains, what you do, you first clean with chromic acid, then followed by water, then you clean with soap or whatever solution, right? So one point where you can see why you are using chromic acid is, why not simple acid or something? Why chromic acid is particularly, chromic acid can oxidize the greasy parts, or like whatever we have just discussed in the last classes. It can oxidize the carbon compounds in the form of grease or any other entities. So what happens? You have a lot of functional groups like carbonyl or COOH groups. Those groups will be washed away by adding water, because earlier as such organic groups are like non-polar or like that properties. You are generating some functional groups, followed them by washing with water. That is the reason why we use chromic acid to clean the glassware. Okay. So now you just give a thought about it. You must have, I don't know whether how many of you have done the practicals because of COVID. Some people might have not have done, but it is very dangerous. As I told, it is a very strong oxidizing agent. Coming back to the class, I think now there is enough strength, like close to 23. What we were very particular about chromic acid versus other oxidizing agents is we can over oxidize primary alcohol into a carboxylic acid, or we can controlly oxidize by using lesser oxidizing agent or removing it with at certain stages. Since we don't have pyridinium, chlorochromate, desmartin, pyridonium, all these things, we don't have this for syllabus. But if you want to make weaker oxidizing agents, if you want to use, you may use this. But what essentially you can understand is you can use potassium permanganate and chromic acid solution, and you can also generate a lot of diols, different functional groups using this kind of precursors. And if you use a secondary alcohol, we may get ketone. Okay. So what are the important points what we discussed in the last class is weak oxidizing agents, they convert primary alcohols into aldehydes. Strong oxidizing agents, they convert directly to carboxylic acids. And secondary alcohols, they they're oxidized towards ketones, and tertiary alcohols, they do not get oxidized at all. So these parts we had discussed in the last class. Now let us look at the reduction aspects. We have looked at oxidation, like adding oxygen functional group, removing hydrogen. Now let us add hydrogen. So many of you are aware already of this particular thing, where we can classify, before we move on to the reduction reactions, let us classify reduction into 4 different classes. Like you can reduce, means you can add hydrogen or add electrons or remove oxygen functionalities. All this, like whatever we had discussed for uh, oxidation, same thing will work hold good for even reduction reactions. For catalytic hydrogenation reactions, we use generally palladium catalyst, and we pass hydrogen gas to a unsaturated carbon. Okay, so what happens? This unsaturated carbon, upon addition of hydrogen, will give rise to saturated hydrocarbon. So what is the important take home for this is we generally use neutral substrates, and it also gives syn addition. Syn addition means adding hydrogen to the same side, here and here, rather than here and opposite side. And it generates a lot of chiral metal complexes. Okay, we should not go more into those details. Next, nucleophilic reduction reactions, where we can add hydrogen. For example, you have an aldehyde or a ketone. To this, we want to reduce this by adding hydrogen. So what we do, we can convert aldehydes or ketones into alcohols. So here also you need to have polarized substrates, like for example carbonyl compounds, and we use for hydrogenating agents as lithium aluminum hydride. Okay? So many of you might be aware of sodium borohydride, lithium aluminum hydride. When we use lithium aluminum hydride or sodium borohydride, where the reactions need not be stereospecific, like for example, syn addition and so on. And you get, for example, asymmetric additions are also possible in sometimes. For example, if you use Corey-Bakshi catalyst. Okay, so again, we do not have so specific reactions for you, but what you should understand is there are 4 different ways by which we can reduce carbon compounds. After the 2 more reactions, we can have electrophilic reduction reactions where we can use, for example, you can have like borane in water, borane and then followed by water. So even here also, you can see how the electrophilic centers of boron will try to anchor to the like negatively charged counterpart of oxygen, and they add, and followed by adding, finally we'll be like reducing all ketones into, or any carbonyl compounds into alcohols. And this is the mechanism by which the reaction follows. Also, we can have radical reduction reactions. Like for example, tin butyl compounds in AlBa catalyst, when we slightly heat, we get uh, replacement of halogen with, or like a leaving group with hydrogen entities. So in all the cases we have seen, we can add hydrogen by these possible methods. Okay, either by providing hydrogen gas, or by using lithium aluminum hydrate or sodium borohydride, or electrophilic reduction, or radical reduction. Now, let us understand how hydrogen as a reducing agent. Okay? So we all know hydrogen gas is very dangerous to handle and so on. So how we can think hydrogen as a reducing agent? We have 2 hydrogen atoms, like 1 electron from hydrogen, 1 electron from hydrogen, or it can exist as 2 electrons and 2 protons. Okay, H plus electron, okay, H plus and electron. So even this is referred as hydrogen, or hydride and a proton. So all these constitute hydrogen. Like for example, H plus plus H minus is H2. Same way with other 2. Now, why these hydrogenation reactions are very important? For example, we have a saturated or unsaturated carbon system. We want to add hydrogen. So what we discussed in the previous slides is, we can add hydrogen here and 1 hydrogen here. So we are saturating it. Even if you have a triple bonded pentane, by supplying hydrogen gas and by using any of these catalysts, platinum, palladium, or nickel, we get pentane. Okay, so even this part, many of you are already aware of, so that we are adding. So please look at the highlight here, which shows hydrogen at what stage it is being added. And if we take butane and 2-butane, and if you want to add hydrogen, we get cis-butene. Now, here we need to use Lindlar's catalyst. Now, can someone tell me what could be Lindlar's catalyst? What do you think the constitution of elements could be, or the composition of Lindlar's catalyst could be? Any idea about that catalyst? If not, I insist you to have a look what it has to do with palladium, or what it has to do with like calcium carbonate and so on. So basically, it's the combination of both. Okay, that is Lindlar's catalyst. Now, how hydrogenation happens? Whatever we have discussed till now, we showed we will have a double bonded or triple bonded system where we are saturating by means of hydrogen. That is what we have discussed. So you can see here we have a unsaturated system. We are adding hydrogen where the addition is syn addition, or if you have a triple bonded, we can also saturate it. Or we have like systems like this C double bond in. Even to this system, we can, in all the cases, if you use metal catalyst. Again, do not all of you worry. This you don't have for your syllabus, but in order to understand the next part, you should get a basic idea about what happens in hydrogenation. So this scheme shows how hydrogenation reactions occurs on this kind of substrates. So we have like metallic substrate of palladium. You pass hydrogen gas. So what happens is hydrogen forms like nascent hydrogen, reactive hydrogen, and then we add the unsaturated carbons when you add the system, where we can the interaction between hydrogen and the double bonded system starts to occur at this place, and once the saturation happens, the molecule will leave the substrate or maybe leave the surface. So this is what happens for um, if you want to see hydrogenation reactions with respect to metal catalyst. Now, what is there for your syllabus? You have lithium aluminum hydride, sodium borohydride as reducing agents with examples. Let us discuss that. We all are aware of the literature that there are several kinds of borohydrates. Borohydrate means BH4 minus, which is depending on how the metal cations, okay, and lithium ligands such as sodium borohydride, lithium, and how the metal cations will react with ligands, either zinc borohydride or potassium trialkyl borohydride or sodium cyanoborohydride. So we have cyano as well as hydrate group and borohydride group. In all these cases, what happens is borohydrates, they reduce aldehydes and ketones into alcohols. But because of the counter cations, for example, Na plus and Li minus, there is some selectivity issues with respect to some functional groups. What are those? Let's see. Now, I would like to ask to all of you, among these two reducing agents, lithium aluminum hydride or sodium borohydride, which one is more stronger and why? Anyone in the class would like to attempt this or answer this question? Which is a stronger reducing agent?
LiAlH4.
NaBH4. For what reason it could
Sir,
be
LiAlH4.
LiAlH4? Okay. For what reason it could be stronger reducing agent? Any reason, Shubharma?
Sir, it reduces everything.
Okay, it reduces most of the compounds, but there should be some reason, right? Compared to sodium borohydride versus lithium aluminum hydride, why it could be stronger reducing agent. Anyway, um, just all of you give a thought about it
Sir,
because
Lewis acid.
yeah, Lewis acid. In both the cases, you have aluminum boron, right? Both are um, both show same type of character.
Yes, sir.
Aluminum has more
Yeah, go ahead, Hariharan. Aluminum has more
reactivity.
reactivity. So now it has to do basically with moving up from boron to aluminum group. Okay, down the group. If you will. Now, how the hydride ion is stabilized? For example, these hydride ions will not be present during the reaction, but they serve as source for hydrides. Especially, you are talking about polar metal hydrogen bond. Also, aluminum is less electronegative than boron because we are moving down the group. And aluminum hydrogen bond, especially in this lithium aluminum hydride, is more polar. So due to which it is a stronger reducing agent than sodium borohydride. For example, that is the reason why we get H minus ion very quickly. In both the cases we get quickly, but the the reducing power of lithium aluminum hydride is very strong as compared to sodium borohydride. So where here also the protonation of alkoxide ion or ketones will be converted into corresponding alcohols. So you can see that why, as we had to, it has to do basically with periodic properties where we are moving down the group, and aluminum hydrogen bond is more polar as compared to sodium boron bond. So like sodium hydrogen bond. Now, this is what, after we discussed about what are the types of reducing agent, why it is stronger. What happens if you want to add hydride ion and a proton, okay, especially to these aldehydes. For example, if you have an aldehyde, you take sodium borohydride in water, we get primary alcohol. Okay, so again, the reactive part of the functional group is shown here. Okay. Where the reaction takes place. So aldehyde is converted to primary alcohol, and the ketone is converted into secondary alcohol. Okay, in presence of sodium borohydride in water. Again, as already we discussed, because of the polarity of aluminum hydrogen bond, lithium aluminum hydride is stronger than sodium borohydride. For what reason we use lithium aluminum? If even sodium borohydride itself is reducing, why we go for lithium aluminum hydride is LiAl5 H4 is used to reduce compounds that are non-reactive with respect to sodium borohydride. For example, we have carboxylic acid. Please take example in the previous case. We have taken an aldehyde and a ketone. Now, we are taking a carboxylic acid and we want to reduce directly to an alcohol. We use lithium aluminum hydride. So we get corresponding to primary alcohol. And an ester, we get corresponding primary alcohol. You see how, where if you use sodium borohydride, it goes to acetal like aldehyde followed by primary alcohol. Whereas here, it directly goes into primary alcohol. Also, we can, with the using lithium aluminum hydride, we can form amines. Okay, so you can see that CO and H2 groups. If we want to reduce, where we can get CH2 and H2. So we can reduce even here, or we can make a secondary amine or a tertiary amine. Okay, using LiAlH4. Again, sodium borohydride will not do this better job, especially if you want to go towards controlled, for example, primary amine, secondary amine, and so on. So we use stronger reducing agents like lithium aluminum hydride. So how it happens? Again, you do not have this part for your syllabus, but people who are interested, they can have a look into this. How, like lithium aluminum hydride, okay, occurs, or it can like reduce how the hydride ion is produced. First thing is the nucleophilic attack by the hydride ion. So you all know that Li plus Al minus. So this Al minus will try to attack this part of the carbon where it is already. You can see here this negative will try to interact here where it is already carbocation. So it forms the hydride will be moved here. Okay, the hydride H minus will move so that it will become AlH3 and Li plus. Now you have this particular entity. It is ionic form. So what happens? The alkoxide ion is protonated because you are using water also, right? So the water part you are taking H plus from here so that it forms alcohol and lithium, the reactive products. So simple terminology if you want to tell. If you want to convert a ketone or any C carbonyl compounds, you can make double bond into single bond, add hydrogen across oxygen and carbon. Okay, so this is a simplistic layman way of saying it, but this is what how the reaction proceeds. Lithium aluminum hydride, like nucleophilic attack, followed by protonation of alkoxide ion. Now, sodium borohydride also is used to reduce selectively an aldehyde or a keto group in a compound. For example, you have like this C double bond O, C double bond O, C OCH3. Like if you have an ester versus this, we can reduce selectively the carbonyl compounds. And if you have a double bond versus carbonyl compounds, it prefers the, so selectivity wise, sodium borohydride also is very good. I don't want to reduce double bond. I want to reduce only the carbonyl compounds. Again, why? Look at the charge generation here, slight partial charge generation, then attack of the nucleophile. If you take lithium aluminum hydride, it even reduces here. Same with here. Both it will reduce. So one part should be selectively reduced, means prefer sodium borohydride. Now, let us conclude this the first half of, or at least the first part of your topic, where if we have lithium aluminum hydride to sodium borohydride, again these both you don't have for your syllabus, do not just worry, but at least look for how like methoxy, toxy, like complexes are present, which are very uh, reactive than sodium borohydride or diisobutyl aluminum hydride. Okay. In the case of what are the important points you would like to take home is lithium aluminum hydride can reduce anything, ketones, alcohol, esters, even like nitriles it can reduce. By even if you want to reduce carboxylic acids into corresponding alcohols, you can do it. Sodium borohydride, on the other hand, it is very selective with respect to aldehydes, ketones, imines. Very, very important point is compatibility of sodium borohydride with water. Whereas lithium aluminum hydride is very, very, very reactive. If we add, it can even explode. Okay, or it can catch fire. Lithium aluminum. So we should take ethanol water or some two solvent mixture to suppress the reactivity of lithium aluminum hydride. Even if you take lithium aluminum hydride outside, you can see it is like very aggressive reaction. Whereas sodium borohydride, it is very safe. Okay. Even that also reacts with moisture to produce hydrogen, but the reaction between lithium aluminum hydride versus sodium borohydride, this is very milder. So these are the important points which uh, we looked at, the how we can reduce different organic compounds, particularly alcohols, two alcohols or amines from the corresponding functional groups, especially using lithium aluminum hydride and sodium borohydride. If you want selectivity, go for this. If you want high reactivity, go for this. Or if you want in between, you may choose this, but let us not discuss more about these two topics now. So, is there any doubt? Anyway, after this, I would like to ask that question. Now, we can have, these are the two reducing agents we use, sodium borohydride, lithium aluminum hydride. You all are aware by now in is nucleophilic substitution reactions and so on, we use the term called ethoxide ion. So how we can, like, ethanol, when you react with methyl, you get ethoxide ion. But even sodium borohydride, these are the preferred solvents where we can use. Like we can use ethanol or aqueous ethanol. You see, aqueous ethanol means you have 50-50 percentage, or if you want to go for a polar substrate, you can take more of 60-40 of more water and less ethanol. Or even sodium hydroxide, dikline. As such, sodium borohydride is basic, so do not use strong acids. What it will do, sodium borohydride, is it can reduce aldehydes into primary alcohols, ketones into secondary alcohols. Otherwise, it is inert. So we have done the reaction. After that, what to do? See, everything will be in the substrate or this one, right? We will have precursors to boric acid salts and so on. By simple neutralization and extraction, we can isolate the product. Isolate the product means alcohols we can take out. In the case of lithium aluminum hydride, we may use ether, THF, avoid alcohols and amines, because it can even, like for example, it can bind with those things as solvents. And also avoid halogenated compounds, of course, strong acids. So it does all this, whatever sodium borohydride is doing the job. But it also reduces esters to alcohols, epoxides to alcohols, nitriles to amines and amides. We have already seen this. Halides, torsilates to alkenes. Okay, so almost all, as someone pointed out in the beginning of the class, it can reduce anything. Okay, I mean, of course, if it cannot reduce which is already saturated, but it does a fair good job of reducing the compounds. What is the processing technique? We should be very careful with respect to water. If you have any trace of water, we should make sure the selectivity and all will change. And removing the aluminum salts. You get a lot of aluminum byproducts in this, which you want to carefully remove. Then finally, extract the product. So these are the standard functions of sodium borohydride and lithium aluminum hydride. So most of the, as we used all this text and all, we used from various books and other sources. Now, is there any doubt on this particular topic, what we had discussed, so that we can move on to two important topics today in the next part of the class? Anyone? Any clarifications needed with respect to hydrogenating reactions? Anyone in the class? Giridharan, Tarun Raj. I hope everyone understood it, or you had any.
No, sir.
Yeah, so no doubts. Okay, so yeah, I hope it is clear for all. Again, if you have any clarifications, you may ask me even at the end of the class, or you can ask.
When
Yeah,
will you send this note?
what is it, Tarun?
When will you post this notes on
Yes,
Google?
today it will be posted. Today it will be posted. Yeah. Again, in this topic, you have only lithium aluminum hydride, sodium borohydride. In the case of oxidation reactions, potassium dichromate, KMnO4. What kind of questions you can expect in this oxidation reduction reactions? Okay. So what is an oxidizing reactions, and what are the types of oxidizing agents? So you should be writing potassium dichromate and potassium permanganate. Give two examples. Same with lithium aluminum hydride, sodium borohydride. What, how, for example, how are you saturating? Take two examples show one example with lithium aluminum hydride, one example with sodium borohydride. Okay. If you want to talk about selectivity and all those, give one example at least to show this is better. Accordingly, it will be there. You do not have any other topics for your syllabus like other reducing agents, other oxidizing agents. You do not have for your syllabus. Let us, yes,
Sir,
go ahead.
possible for is it possible for you to send some extra questions based on this chapter?
Yes, I will. I will inform you. We will also um, tell you at the, because I don't know at what stage you want. Probably um, during the lab classes, or even once we finish the second unit, and then we are last 5-10 minutes we'll discuss. Probably from second day order, tomorrow's class also we may discuss what kind of questions. Because as I told, we do not want to give you straight away the question bank right now. Okay.
Okay.
We will, all of you, if you read, see, even question bank also, you will be having each, for example, oxidation reduction reactions, 4 questions. What are the oxidizing agents? Give example for each. Discuss oxidizing reduction reactions. Okay. They will ask also, you can write a note on lithium aluminum hydride and sodium borohydride. Essentially same. If you understand like that, if question bank compasses lot of um, questions, but what I am telling you in every class, this is what you can expect it when you write. Okay, even though I teach for, like, we teach for almost 20 minutes, what this should be done in the class is only half of the class I should discuss this. But if I won't teach you, all of you, how the hydrogenation reaction happens, okay, you at the hydrogen interface, like for example platinum substrate and all, you won't really appreciate, uh, for example, why selectivity, all those things issues comes. Okay, that is the reason we are going elaborately. Okay, but the material what we give you even has slight extra points, but if you read and write, it is more than sufficient. Okay.
Sir, can you give any sample questions for the
Yes.
12 mark question?
Yes, I'll definitely I'll post it. I will we'll discuss it. I do not want to post right now in the Google Classroom. We'll discuss that. Only thing is, I'll share it through this, or I will give some points, so where all of you can take down. That is also one good suggestion. I don't want it should be posted in the GCR at this stage. Definitely after your cycle test 3 or before that, the question banks will be posted, and already in the last semester and all we used to do that. We used to post the question bank, since it is um, what is more like MCQ type questions. 12 mark questions, 4 mark questions were not at all used before. Definitely question banks will be shared with all of you, and for your final exams or all those things, you'll be getting questions only from that. Again, that is not one or two, you will be having more than some 100 questions. It's essentially all the topics. But I will, as I told, I will, as promised, I will give you, or I will give some sample questions either by sharing here so that you can take down. That will be more appropriate. Yeah. At this stage, do not. I don't want to post in the Google Classroom. Okay. One best example of 12 mark question we can, or a 6 or a like 12 mark question which can have 2 parts is discuss about SM1 uh, mechanism, followed by or which are like oxidizing and reducing agents, 8 and 4 marks, or what are the possible conformations of cyclobutane, what are the conformations of butane. Okay, such kind of questions you can expect. Anyway, I will give you those questions in tomorrow's class also, so that you can start thinking about it.
Sir, can you post the syllabus thing, that is a unit which has the subtopics and the credit things and all will be question, sir.
See, you will have definitely from second topic and third unit equal distribution. Okay. Um, you will, that's what I told. Both second and third unit will come. In that, what are important? Like for example, second unit where we had a lot of thermodynamics and everything. As I told, Pourbaix diagram is one such question. Is a very important, and types of corrosion you can expect for 4 marks or a very short, at least what are the different types, or even it can be countered with an essay type where what are the different types of corrosion and how to control it. Okay, Nernst equation derivation. So these are all like important questions. Same with inorganic chemistry, what we are going to discuss, like how to convert Fischer to, or like butane conformations, all those things. Yeah, I will, don't worry, for all of you, I will share it. I don't want to post. Please take down. At least if one of you take down or like that, you can even share with your friends. But definitely, I will post the question bank. Even after seeing the question bank, you will not be very happy because there are so many questions. Okay. It's very easy if you understand the concept and what to be read, and also what I usually tell in the classes. Such questions will be asked that you can make a note. And also we'll discuss one class before your exam, or at least before, on what topics we can highlight. Okay. Now, let us look at two more topics, or for example, an important topic today. We still have second hour to go. I hope you can see the slides.
Yes, sir.
We are now looking at two important reactions. Like this topic followed by, this is a very short topic. This will be followed by the next part of the reaction, which is ring opening reactions. Till now, what you have seen is substitution, and then what we have seen second half is electrophilic reactions and addition reactions and so on, where we are just substituting, adding, and so on. Oxidizing reduction reactions also we have seen. Now, let us make a cycle, or make an acyclic system into a cyclic one. So simple. For example, convert. You should make a cyclohexane kind of entities rather than hexane. One such topic what you have is Dykman condensation. Sorry, Dykman cyclization or condensation reactions. How many of you already studied in your earlier classes about this? About cyclization reactions?
Yes, sir.
Already you had studied Dykman condensation too, Shubharma?
Ye- Yes, sir. I've studied about it.
Okay, fine. Yeah. So let's see what happens in Dykman condensation. Um, for the new people who do not have this topic, let us, before we proceed to Dykman condensation, let us understand what is, how we form a carbon-carbon bond. Okay. So we have carbonyl bonds and OR groups, like ester. If you take two different kinds of esters, and you take sodium alkoxide in acidic medium, where we are replacing this OH and forming this carbon is being attached to it. Okay, so we create beta keto esters along with alcohols. Why are we talking about this in Dykman condensation? Now, before we understand Dykman condensation, let us see what is Classen's condensation. What is Claisen condensation is, we are looking at carbon-carbon bond formation which happens between two esters. We take two esters and we form CC bond. in the presence of strong base like alkoxides, where we get beta keto esters or beta diketone. You have two ketone groups. So this is Clason's condensation. What Clason condensation has to do with respect to what is in your syllabus? Again, when they ask you for a Deichmann condensation, you need not write about Clason condensation. But first of all, you should know it has to do with removing OH or OR and adding CC bonds. Just remove this, okay, and add this part to here. Now, one of the reagents we should be having enolizable, okay, where that enol keto, that composition you are aware of, especially proton which can undergo deprotonation, particularly alpha proton, which is bonded here. Once this goes, we get enolate ion. Okay, so that is the basis for the Clason condensation reactions. Again, you should use a base. Okay, base should not interfere with respect to addition or substitution of carbonyl cation. So this will not come and substitute, or it will not add, saturate this, okay, with respect to carbonyl carbon. So the base should not affect esters. The such kind of things you want to take. Let us see how this happens. How CC bond takes place. Again, this part you don't have for syllabus, but you should understand this. Only if you understand this, you will understand Deichmann condensation. You can see here in ester, we have sodium ethoxide and aqueous hydrochloric acid in ethanolic solvent. What happens is, if you do this part followed by working up with this, we get, as we know, a diketone along with ethanol. So the first step is how alkoxide ion deprotonates the enolizable ester. So we can see that this alkoxide ion is there, like, so Na plus ETOH minus. OET minus would like to take away the proton from, like, a enolizable part. So it takes away this. So we get ethanol along with this, will be having electron rich in that case. So this will be like minus, and the hydrogen electron also will be coming here. So it forms this stage. It will be like anionic in nature. Now this reacts with one more equivalent of the ester. Okay. It reacts with one more part of this equivalent. So what happens is, here also you create the carbonyl bonds, means it become more negative here, and this will be positive. So this adds to here. So where you are creating CO bonds into CC bonds along with O. Simple step after this, we add little bit of acid to make OH. So step 2 and 3, where enolate ion, what has been formed in the previous case, it undergoes in acyl substitution, means acyl group is being added here to give beta keto ester. Okay. Finally, this can rearrange into double bond, and the ethanol will be leaving to give beta keto ester. So this is how a CC bond is formed, and it has to do with Clason type of condensation. Now, let us come to your topic, what you have, which is Till now you have seen everything was nice. Okay, uh, we had like this, we formed this. Let us cyclize means instead of extended system, let us cyclize it. If you want to cyclize, for example, you take diethyl hexadiodate means you have two ethyl groups, six carbon membered ring with carbonyl and again it's also an ester. Add sodium methoxide with aqueous hydrochloric acid mixed. We get, we are closing it. Now you see OET has gone and we are making a five membered ring. Take six membered carbon, make a pentane carboxylic acid. So this kind of reactions are referred to as Deichmann condensation. So what is Deichmann condensation? Is if they ask you, generally such questions can be asked for 4 marks. Deichmann condensation is intramolecular chemical reaction, means within the molecule. So intramolecular, within the molecule only, this leaves and this rearranges to give five membered ring. Okay, so this carbon comes and attacks here, and where intramolecular chemical reactions of diesters which gives rise to beta keto esters. This 1,6 diesters, especially some this kind of situation, they give rise to five membered cyclic beta keto esters. If you have 1,7, you will get six membered. If you get six carbon system, we end up getting a five membered ring. Seven carbon system, we get six membered ring because one carbon less to close the ring, because we are forming a CC bond. Now, for all of your convenience, you may look into this slide where this diester you have, okay, this diester using sodium ethoxide. How, again, you do not have mechanism for your syllabus, but people who can understand why it happens. You can see this ethoxide unit will be cleaved, or ethoxide ion will be free, and you can see the carbon will charge how it creates, and then it forms a uh, pentacoordinate, like for example, five coordinated system like this. Once the ethoxide ion will be again lost, okay, and then you will get carbonyl compounds. So this is how a six-membered carbon system will give a five-membered cyclic CC bond formed system. Okay, where the ethoxy group will be cleaved and then it connects to form the corresponding bond. Okay, so this is all about Deichmann condensation. Now we have only seen about five membered ring. What happens, especially for how to summarize this? Deichmann condensation is intramolecular version of Claisen condensation. What in the case of Claisen condensation is two different molecules. In the case of Deichmann condensation, it is within the same molecule, so it is intramolecular version. This generally works well with 1,6 diesters or 1,7 diesters. So bird. So this is how the Deichmann condensation works. Now let us see a little bit carefully on how this reaction works. Do not worry about for time being this. I will show the important animation here. So how sodium methoxide, when it comes, how the proton cleaves, and there you get the charge. As soon as this carbon, like carbocat anion kind of thing, will immediately try to attack the carbocation here, or partially formed carbocation, and then you rearrange where we get ethanol will ethoxide ion will be lost, and you rearrange and make a like workup where you add a proton here, and then you form the water along with this particular product. What is the important point with respect to this is deprotonation of ester at alpha position, especially alpha position, which creates an enolate ion, which makes it to pass through nucleophilic attack. Like after such steps, you get cyclic enols. Okay, where we have double bonded along with carbonyl system. So here you can see how the reaction of animation of the reaction mechanics. So you have system like this. So we can alkoxide ion will come, and you see how it binds to here. Alcohol will be gone, and you create a double bonded system. And once if you are working up with the last part, it saturates, and you can see this is the formation of beta keto diester. Okay, so this is all about the Deichmann condensation reaction. So these are the two important sets of reaction what you should be aware of. If when they ask you to write about, first if you write it's about Claisen intermolecular version of Claisen condensation reactions, give example of this or this. Okay, and accordingly we can summarize it. Okay? You may take down this particular part now, take down, and we have last topic to be discussed today. We shall take like I will take attendance in the meanwhile. Yeah, I don't know why it got sharing got stopped. Sorry, but yeah. You may take down this two reactions, and I shall take in the meanwhile attendance. Rakesh. Rakesh is around. Okay. Ileraj.
Present, sir.
Rakesh present, sir.
Yes, yes. Okay, okay. Shashank.
Present, sir.
Tarun Raj.
Present, sir.
Harish.
Present, sir.
Srinivasal Reddy.
Present, sir.
Satvika.
Present, sir.
Amitoj.
Present, sir.
Okay. Ayappa Reddy.
Present, sir.
Hariharan. Sorry, Hiridaran.
Present, sir.
Ramchandra Rao.
Present, sir.
Anurag.
Present, sir.
Shubh Verma. Shubh Verma was present, right? Okay. Karthik.
Present, sir.
Shas.
Present, sir.
Hariharan.
Present, sir.
Surya R.
Present, sir.
Sai Kumar.
Present, sir.
Uma Venkat Reddy.
Present, sir.
Rudresh. Rudresh is around, I guess. I saw him. Yes, Uday.
Present, sir.
Yesh.
Present, sir.
Surya A.
Present, sir.
A. And yes. And also like Manish is around.
Sir, present, sir.
Yes. Okay. So I don't know. I see today 26. Is there anyone who joined with both phone and this, or a new student has come? I don't know. Anyway, So I hope you must have taken down this. And today at the last 5 minutes or 10 minutes of the class, any clarifications, any doubts with respect to the presentations, we will discuss. I think already 5 people I have emailed yesterday. We will discuss about that at the end. Okay, those people can stay just for very briefly for even 2 to 3 minutes also. Now, is there any doubt with respect to cyclization reactions? Again, what you can expect in the cyclization reactions questions are discuss about cyclization reactions, especially Deichmann condensation means you should write about intra-molecular Claisen condensation reaction where we are forming CC bonds and give these two examples. Okay, why that beta diketo esters or esters are formed. If you write, that is more than sufficient. You can straight away get 4 marks. Generally, they won't combine this 4 mark question only it is, or they can ask you for 12 mark means 8 and 4 marks. 8 marks some other question, okay, and 4 marks for this. That way they can ask, but it's essentially a 4 mark question. Is there any clarification doubt on this particular topic? Yes, or you are waiting for the handout to be shared today so that you can go through it and then ask. I will post the handout today so that you can have a look into that. Any doubt, or can I move to the next and the last topic for today? Uday, Rudresh.
No doubt.
No, no. Okay, so I guess it's no for others too. Uday and Rudresh, any doubts or clarifications?
No doubt, sir.
Clear.
Okay, okay, fine. Yeah,
Sir,
again, yeah,
small
yes.
request.
Yeah, I will discuss about the model questions. Don't worry.
No, no, sir. Can you share the probatic diagram videos recording?
Okay, okay. I'll share. Yeah, I will share with you, and you can share with others whoever needs. Okay, but just remind me. Okay, in WhatsApp or like that, I might forget. Just remind me. I will post it to one of you so that you can be editor and you can share with others. I
Yeah,
don't want
sir.
to put in the GCR. Okay. Yeah, okay. Let's see. The last part of today's reaction is ring opening reactions. What happens when you react cyclopropane with all such systems? Let us see. By now, you all know what is cyclopropane. Can someone tell me few properties about cyclopropane? I have shown the structure, but what are its important properties of cyclopropane? Anyone in the class? Essentially, it looks like this. Okay, I will tell you about that structure more in detail, but what you are aware of cyclopropane?
Stable, sir.
Stable. Any other thing? It is not very stable actually. Okay, it has to do something with stability part. That is also one point we can consider. How many of you have heard this before? Cyclopropane. Or is the first time, because many of you might have heard about cyclohexane, right? Cyclobutane or higher forms.
Sir, in organic chemistry classes in 12th, 11th.
You heard about cyclopropane too?
Sir, I heard the name of the molecule, not studied about.
Okay, properties. Okay, no, no, not a problem. Even see, even if you have any one of you have read it, even if you forget, it's not a problem. But what is my question is, what are the important properties you heard of it? I mean, if at all you had the class. If not, let us discuss. No problem. Let's see. This is cyclopropane. Essentially, you have saturated carbon bonds. It is cyclic, you don't have, it's not aromatic, and it forms system like this. This is the smallest alkene which can form a ring. Okay, if you have only two carbon atoms, you cannot have a ring. Obvious. This is the smallest alkene. That is the reason it is a smallest alkene which forms cyclo a ring. And the three carbon atoms, they are lying in the same plane. I hope, I don't know how many of you can see clearly because I am seeing the presentation. You can see this black are carbons, 1, 2, 3. These all carbon atoms are in the same plane. Okay, they are all in the same plane. You can, now we can really appreciate this. They are in all sorry, same plane. Okay, and what are its properties? Like this is about geometry. In the case of cyclopropene, it's a colorless gas and it is sweet smelling gas. Okay. Now, the most, if at all, some of you or a few of you might have studied with respect to cyclopropene is, it is known for its ring strain, okay, as compared to acyclic hydrocarbons. These cyclic hydrocarbons, they have within themselves a ring strain. Why this ring strain happens is because of torsional strain versus angle strain. Okay. You might wonder what are these strains okay, in molecules. Okay. You all by now are aware of tetrahedral structure of carbon. Like if you take like functionalized methane or like that, this is what you get. Right? You have carbon tetrahedral. So again, these are in one set of plane and these away from you. Or for example, this orange is towards you and green is away from you. You can consider. Okay, and red color is on top. So this is a conventional geometry, what you are all aware of. But this kind of strain, you see, if I, this is the structure, okay. If I want to connect to this carbon atom, you see the bonds are not straight, they are bent. All of you can understand that? Yes?
Yes,
Yeah?
sir.
No. So you see as compared to these bonds, if I want to put one more carbon atom here, okay, if I put one more carbon atom here or one more atom here and then connect these two, there is no strain, but you can see here so can someone tell me what kind of bonds are these kind of bonds called? You might have studied in with respect to other molecule which are bent. You can see this molecule. What kind of bonds are called when they are like weakly held or very strainedly held molecules?
The van der Waals
Banana
force.
bonds.
Banana bonds. Van der Waals is more to do with very weak interactions. But now this can be like you must have heard like tau bonds or banana bonds, something like that. Let us see what these things we are talking about. By what you understood now is smallest number of carbon and there is a lot of strain. You see, we strain the molecule to form and there is no longer a standard geometry. So we get torsional strain and angle strain. Angle also is strained and because of the twist we also have a strain. So this is, you can see if you show like a projection formula, this hydrogen is pointing you and broken bonds are away from. Now Cyclopropane, you have a planar structure where the bond angle between carbon-carbon, between this carbon to this carbon, they are at 60 degrees. Here, here, here. Again, 60 degrees is less as compared to tetrahedral geometry. Sorry. This is less as compared to tetrahedral geometry. How much less? 40 degrees or something. Because of which we get ring strain for cyclopropane. And also because of this angular strain, cyclopropane also suffers from torsional strain. When angles is strained, when angles are strained, there is also torsional strain. Again, why it occurs? Because the coplanar arrangement of carbon atoms, where we see the eclipsed arrangement. Okay, you might be wondering, why are we talking about eclipsing of hydrogens, that to Newman projection for a 3-carbon system? Okay, we have already looked at butane, but why cyclopropane? How to draw that? Let us see. Before we move on to the other parts, this is cyclopropane, butane, pentane. We are very familiar, everyone. Cyclohexane, heptane, and octane. If you look at the bond angle, 60 for cyclobutane, 90, pentane 108, 109 till 135. The strain energy, okay, it should be, I think, strain, which is misspelled, or it is also referred for some, okay, as 114 kilojoule per mole. Cyclobutane, it is 110. It has reduced. And for cyclohexane, it is 0. No stable form. Cyclopentane, it has reduced almost to 5 times or even 4 times with respect to cyclopropane. So you all by now understood it is very strained molecule. Once it is strained, what happens? It wants to react. How it needs to react is by breaking the bonds. Okay, so I don't know which one I want to remove. Okay, somewhere I want to, yeah. So it wants to break the bond because it is so much strained. So once it breaks, then it will be more stable. Now, if you look at the bond angles of propane, cyclopropane, and cyclobutene, if you look at propane, it is 109.5, only propane, not cyclopropane. Whereas here, cyclopropane, it is 60 degree, which is 49 degrees lower than 109.5. And the cyclobutane is 19 degrees. That is the reason this strain is lower than here, but still there is a strain for this. Now, let us see the Newman projection, how to draw torsional strain. So you can draw like 3-membered carbon ring as where you are seeing. You can see from viewing from this direction. This part is away from you, and this is towards you. Both the carbons are towards you. 2 and 3 are towards you. So what do? You accordingly write. You are seeing the CH2, hydrogen, hydrogen, and this back part you are going to write here, 2 hydrogens. So now you can see here these hydrogens from the front carbon is here. We are putting a dot, and these are the rare hydrogen. There is an eclipse. It means hydrogen are eclipse, due to which you also get torsional strain. You already saw angular strain. Now torsional strain, due to which it is very reactive. Now please look at the bonding. The CC bonds as compared to the cyclopropane with other systems, they are bent, and they are no longer sigma bonds. Again, it has to do with pi orbitals, how they overlap. So it is not even pi orbital overlap, neither sigma bond overlap. So what happens between such systems? If you look at the p orbitals of carbon, how they are overlapping. In that case, they are in between sigma bonding and pi bonding. As already Anurag pointed out, this we have to do with calling such bonds as banana bonds. So this is how the structure what I have just now shown you looks like. How strained it is, you see, in all the places. Okay, so now this is about, you know that now there is angular strain and torsional strain. If you want to look at the removal of that CC bonds and then to react about the carbon atoms, especially in terms of bent bonds, so that the inner orbital angle is 104, due to which we also get bond strain. So these are also called as banana bonds because the connection between CC bonds are in between sigma bonds and pi bonds. So you can see how the interorbital strain is there and what is the interangular strain. You see how it is very strain molecule. This strain in cyclopropane will lead to its reactivity to break the CC bond or to cleave the chain, which brings us to the reactions. So this you can also expect for a 6-mark question. Okay. Discuss the reactions of cyclopropane with 4 examples. So first what you want to write, you draw the structure and talk about torsional and angular strain. Then you go for the reactions. Let us see. You have cyclopropane. Again, recap till now. You might ask me, you were talking about ring opening, but then now there is no ring opening. Why? Because in presence of UV light, this cyclopropane will undergo substitution reactions. Substitution means substitute hydrogen with one more. That's all you are getting. But it can react only in the dark. In dark conditions, if you take this reaction, we get bromocyclopropane. One hydrogen is replaced with bromine and then HBr. In the absence of UV light, the cyclopropane will undergo addition reactions. Addition means here one bromine, here bromine. So this should definitely cleave. In that case, we get dibromopropane. You can see. Again, in the absence of UV light, you see addition reactions where it undergoes like this. So bromine will be added here and here so that this will form the center carbon atom. So we are looking at the bond cleavage, like cyclic system is broken. Now these are the reactions which it is very straightforward what you can expect. So you, in a nucleophile, you generate slight positive, slight negative charges because of electron destabilization and or any hydrogen halide or like that. And then you add to the corresponding system. Whereas in this case, you add, if you cleave the bond, you add X here and Y here accordingly. So what are the reactions you have for your syllabus? Is cyclopropane reacting with bromine, with hydrogen, sulfuric acid, hydrogen bromide. In all the cases, these are mostly do with electrophilic attack especially the reactions. And you get cyclopropane means sulfonic acid functional groups. So 3 membered carbon with sulfonic group and bromopropane. Okay, where hydrogen gas, if you add to cyclopropane, these bonds are broken to form propane. It will saturate. If you add bromo, you get dibromo in the absence of UV light. So you may look for animation how this reaction works in this website. Okay. Now we will conclude this class by the reactions. Hydrogen bromide, how it happens. Okay. If you add hydrogen, we get. You may draw even like this in your exam. So for this you can get 6 marks. But before that, you should talk about what are the different. Here it should be SO3H. But you remember we are already working up with water. If you only take sulfuric acid, you get SO3H. But we are working up with water, so we get OH. And chloro or bromo compounds, we get corresponding dibromo, propane, respectively. So these are the important points which we can close for the class. In today's class, we discussed about cyclopropane reactivity. In the next class, we will look at drugs and medicine. Okay. Already the video lecture is already being shared in the Google Classroom. If you are interested, you can look into that material as well, along with the video lecture. Along with that, I will discuss in tomorrow's class about 2 important reactions what we have for your syllabus. Then we are almost at the end of the unit 3. After this we are going into macromolecular structures, which is from the after 2-3 classes also. Okay. Is there any doubt with respect to this particular topic, cyclopropane reactivity? Yeah, already I think we had discussed today 3 important topics. I don't know whether it is too heavy or the topics, but I feel cyclopropane and Deichmann condensation are relatively simple. Also the hydrogenation reactions. Is there any doubt?
No, sir.
Okay. So I will, as still here, I will upload the handout. You may look into that and accordingly prepare for your exams and other things. As I told earlier also, we will, as soon as I get information regarding the pattern of the exam, I shall immediately share with